Hi everyone, my name is Zishen. Today, I'm very glad to present our work, an energy-efficient quad-camera vision system for autonomous machines on FPGA platform. This is a collaboration work with Georgia Tech, Beijing Institute of Technology, and Perception Corporation. First, please allow me to briefly introduce myself. I'm a first-year PhD student at the Georgia Tech Electrical and Computer Engineering Department. I have a research interest in VLSI design, computer architecture, machine learning, and edge intelligence, with a focus on energy-efficient and reliable hardware and system design for autonomous machines. I received my master's degree from Harvard University in 2020 and a bachelor's degree from Harbin Institute of Technology in 2018. This is the executive summary of my talk. So first, I will show you that the vision system is the compute bottleneck of autonomous machines and a lucrative acceleration target. Next, I will analyze the algorithm blocks in ORB-based vision system. And then, I will present you an energy-efficient quad-camera vision hardware architecture on FPGA platform, and several design optimization techniques are proposed here. And finally, I will show you some evaluation results that our FPGA design achieves up to the 5.6x speedup and 34.6x energy efficient improvement. So the visual system is the compute bottleneck of autonomous machines and a lucrative acceleration target. As we know, in the past few years, we have seen a rise of autonomous machines, and they come into the different forms. For example, we have the robotics arm, which are extensively used in factory. And we also have the drones that can be used for the package delivery and scanning. And to a larger scale, we have the self-driving cars. However, there are challenges that make these robots autonomous. First, let's go through the key steps of autonomous navigation. So these are three key blocks. The first is perception and localizations, which determine where you actually are in the environment. So it lets us recognize the environment and recognize the obstacles and locate yourself. And once you know where you actually are as a robot, the next step is the motion planning and determine where you want to go in the next. And finally, you have controls that send the control commands to the actuators that move the robots to the desired location. And out of all three compute engines, the perception and localization tends to dominate the computing bottleneck, especially with only camera and arm use. This front-end must precisely perceive the obstacles in a known environment. And moreover, the efficient visual and localization system is a prerequisite for the further exploration tasks. So let's take a closer look at the front-end. As we know, the hardware design must target on critical and compute-intensive blocks. So to understand the role of the front-end system, we analyze three popular localization algorithms here, named SLAM, VIO, and registration. And these algorithms are adaptable to different scenarios. For example, the SLAM, the simultaneously location and mapping, is usually used in the indoor unknown environment. And registration is usually used in the indoor known environment. And the VIO, the virtual inertial odometry, is usually used in outdoor environment. And generally, the localization consists of a virtual frontend and optimization backend, as shown in the top right figure. The frontend extracts the vision features to find respondents in observations, while backend estimates the pose and updates the map. All three localization backends can share the same vision frontend. And here, we use the ORB vision frontend, which has been widely adopted in the robotics community. And by measuring the average compute time of each module, we show the runtime distributions between the visual frontend and optimization backend of the localization system. Interestingly, we notice that the vision frontend is the system bottleneck of the localization system, and it varies from the 15.5% to 87% in these three modes. And therefore, we conclude that the vision frontend is a lucrative acceleration target And since the different localization algorithms usually use the same image processing approach, accelerating this visual system would lead to a universal performance improvement. So now that we know that the vision system is the bottleneck, then what algorithm blocks are inside here? Usually, the vision frontend consists of the feature extraction and feature matching stages, where the feature extraction is used to extract feature descriptors from input images, and feature matching is used to calculate the disparity and depth information based on extracted features. And let's take a closer look at each stage. So we use the ORB for the feature extraction. So ORB is an abbreviation of the oriented, fast, and rotated brief. So it is the efficient fusion of the fast feature detector and brief feature descriptor. So there are two steps in the feature extraction. First, we use the oriented fast to detect feature points in the image and ensure their rotation invariant and scaling invariant. And usually the points that differ greatly from the reference point's intensity are detected as the feature points. Next, we use the rotated brief, compute descriptors of feature points, and also get their intensity and orientation information. And for the feature matching, it usually consists of two steps, the stereo matching and rectifications. So the stereo matching step matches feature points in the left-right image pair with the smallest Hamming distance. And since the stereo matching with ORB feature is a local mapping algorithm with fast speed but a high mismatching rate, we use the SED rectification to correct the coordinates of the feature points. And then the disparity and depth information is calculated based on adjusted positions. So after analyzing the key computational kernels, next I will present our energy-efficient quad-camera vision hardware architecture on FPGA platforms. And to efficiently mapping these algorithm blocks to the hardware and achieve the high performance and low energy consumption, we propose the several design optimization techniques here. So first, I will show you the overall architecture of the proposed vision system accelerator. So 4 cameras and MU interface with the onboard compute. And the front-end vision system is implemented in the FPGA to accelerate the feature extraction and feature matching. And the CPU is used for the backend optimization computations. And to improve the performance, we propose the hardware-based synchronizations, detect I/O architecture, and the frame-multiplexed schemes. And I will talk about these details in the next few slides. So first, the hardware synchronization interface. Because we know the synchronized interface between the sensors and computing modules is very, very crucial for the autonomous machines to correctly perceive the surroundings and localize itself. However, in the whole system, the software synchronizations in CPU leads to the variable delay among the 4 images, making it impossible to achieve the reliable localization results. So to solve this, a stable synchronization issue, we propose a hardware-based synchronization. First, all the captured images are directly sent to the on-chip RAM through our direct I/O architecture. And the trigger generation module generates the synchronized trigger signals for the cameras and IMU. Second, both the input images and IMU data are tagged by a unified time tag. And finally, the images and IMU are synchronized at the interface with stable time tags and then sent to the computing modules. So this can significantly help achieve stable feature processing and localization. And next, I will show some of the architecture overview of the vision frontend. So here we propose a frame-multiplexed scheme where 2 camera channels share 1 feature extractor. So the rationale behind this is based on our profiling result, the feature extraction takes around 7 milliseconds, and the feature match takes around 40 milliseconds when processing the 614 cross 418 images. So that indicates the latency of the feature match is twice of the feature extraction. Moreover, the two identical hardware modules are designed to process two stereo cameras in parallel. And this is the utilized processing pipeline. As you can see, the two images, which means the left and right image, are captured at each frame. And during the processing, like at nth frame, the feature extractor first processing the left image and stores the result in the buffer, and then processing the right image. And after the extraction is finished, the feature descriptor of the image pyramid are sent to the feature matcher for the disparity computation. And when the feature matching at the nth frame starts to work, the feature extractor is sped up to process images for the next frame. So with this frame-multiplexed scheme, the feature extractor and feature matching module could be performed efficiently in pipelining. And the vision frontend runs in parallel with optimization backend. So this scheme significantly saves the hardware resources and also improves the throughput. And next, I will show you some detailed architecture of the feature extractor. So the feature extractor blocks extracts features from images. So it reads data from the image buffer and calculates the ORB features with on-chip memory. And after the task is finished, it sends the features to buffer and descriptors the feature matcher block. So the feature extraction architecture consists of the image resizing module, the fast detection module, orientation computing module, image smoothing module, and descriptor computing modules. Let's go through them one by one. So for image resizing, it's used to build a two-layer image pyramid with the bilinear interpolations. And the fast detection module takes the patch from register bank as an input and detects the feature point and computes the moments of the patch. It stores the coordinates of the feature points in the VRAM. An orientation computing module takes the intensity centroid of the patch as input and calculates the orientation of the patch and then stored in the RAM. An image smoothing module utilizes a Gaussian filter to smooth a 7x7 pixels patch stored in the register bank network. And descriptor computing module takes the smoothed images, coordinates, and orientations of feature points as input, and then determines their descriptors. So here there are two main design optimization techniques I would like to highlight here. So first, the orientation computing module involves division and square root operations that require a substantial cost. So we adopt the word length optimization method and choose the 8-bit to reduce the hardware consumption. Second, during the descriptor computation, to avoid the smoothed images occupying too much memory, we adopt a synchronized two-stages shifting line buffers to compute Gaussian filtering and descriptors in a streaming way. And next, I will go through the feature matcher block. As you know, the feature matching block aims to match feature points from stereo images and derive the depth information. So the detailed architecture of the feature matching includes the several search region decision module, the distance computing and comparison module, and also the correction and disparity computing modules. Let's go through them one by one. So for the search region decision module, it takes the coordinates of the feature points as input and determines whether the feature points locate within the searching field. And for the distance computing and compare module, it obtains the descriptors from the RAM and computes the hemidistance of each pair of the feature descriptors. It then finds out the best matching with the smallest value of the hemidistance. And the correction and disparity computing module is used for the SAD rectifications. It takes the coordinates of the matched feature points obtained in the stereo matching and patch image pyramid from the register bank, and computes the corrections and disparities. And the depth information will be sent for the backend to use. And here, I would like to highlight one design techniques we used here. So we utilize an image pyramid multiplexed scheme during the implementation, where two residing images share the same feature matcher block that can significantly save hardware resources cost. Finally, let's look at some of the evaluation results. So our proposed vision system accelerator is implemented and evaluated on the Xilinx Sync UltraSpeed Plus MPSoC. So the FPGA is directly interfaced with the 4 cameras and IMU sensors. The max operated clock frequency is 203 MHz for feature extractor and 230 MHz for the feature matcher. We evaluate the resource consumption of design on 2 different image resolutions. So overall, you can see the hardware architecture utilizes around the 51% lookup table, 12% flip-flop, 30% VRAM, and 1% DSP resources when processing the 640 cross 480 images. Particularly, we can observe that the feature extraction consumes over 2/3 of the front-end resources in both images, which further corroborates our scheme to multiplex the feature extraction module between the left and right frames. And we also evaluated the accuracy. So the accuracy of the system is evaluated by the results of the feature extraction and matching between our FPGA and MATLAB software implementation when processing the 30 frames. And we can see that the error is within the 0.3% for the number of extracted feature points, matched feature points pairs, and also the obtained depth values. We also evaluate the performance and power of our FPGA design. So we compare the results with CPU, GPU, and existing accelerators. So for the CPU and GPU, compared with Nvidia TX1, the performance is raised by around 5.6x, and the power is reduced by the 67%. And compared with the Intel i7 CPU, the performance is raised by the 3.4x, and the power is reduced by the 97%. And for existing accelerators, compared with designs in FPT paper, we achieve a slight speedup for the 64% power reduction. And particularly, we propose the actual stereo matching modules for the depth information, which is very vital in the 3D environment. And compared with the FPGA design in the deck paper, we achieved a 1.23x speedup and saved the 60% power. However, we support the multi-channel camera systems with proposed hardware synchronization scheme. So to summarize our work, we identified that vision system is the unified compute bottleneck of various localization schemes. And we propose an ORB-based real-time and energy-efficient vision system for autonomous machines on FPGA platform. And we present a hardware synchronization scheme to support multi-image channels and IMU for reliable localization. And several optimization techniques, including the frame-multiplexing, parallelism, and pipeline, are exploited to reduce the accelerator latency and also the energy. And compared with the Nvidia TX1 Intel i7 CPU, our design achieves a 5.6x and 3.4x speedup in frame rate, and 3x and 35x improvement in energy efficiency. With that, I will conclude my talk. If you have any questions, please feel free to reach out to me. The contact information is shown here. Thank you for listening.